I didn't really have this little segment planned, but if you'll take note of this silk screening for, this is Q3, which is an NPN. You see that the flat line in the silk screen is facing this flat line. This is Q4. It's also an S9011. We have two other devices. The flat face, you can see it here. And you can just barely see it here, there. So it would appear that these, if you will, are facing each other. And this is facing each other. Now, when I drew the schematic of this board, of course, it was not populated. So I used a magnifying glass and a nanometer to get to point-to-point connections. Then I dropped into my schematic the components based on the silk screen. This is an abbreviated schematic of the events occurring around Q3. And this is what I came up for as a schematic. And I could not reconcile this. Like, in my mind, I don't know how it works. I also noticed as I drew the schematic, this was very close to the 3 amp, 30 volt Chinese supply that's everywhere. So I did some research and I determined that this is the correct schematic, where Q3 has an emitter connected to power negative, the collector connected to the base of this first Darlington stage, and then it's biased by these two transistors from power positive to minus 5 volts. If you work out the voltage provided by this voltage divider at the base of the transistor, you find out it's virtually nothing, 0. That transistor in a properly operating supply does nothing. However, if the minus 5 volt rail were to disappear, that transistor would be heavily biased through R18, and conduction would occur between here and power negative, pulling down the voltage here, which would fold back the output voltage, because the output voltage is essentially the voltage here, normally controlled by the output of U3. So this does nothing if the minus 5 volt rail is in existence. The problem is, with this minus 5 volt rail, is it powers both of the TL081s. One controls maximum current, the other controls voltage. Without the minus 5 volt supply, both current and output voltage become indeterminate, and probably, in fact, will go to max. This is the way the silk screen appears on my circuit board. I believe that this is how Q3 needs to be inserted. Not this way, but this way. Now I should say there's no revision number on this board. There is, I believe, to be a board maker number there. So if you get one of these boards, you'll have to check out Q3 with an ohm meter. I'll label this little notes I'll put the board number of the incorrectly marked board. You could have a later or an earlier version. And I'll include this in the infamous subdirectory noted below. In part 2 of this series, I talked about adjusting R19 to give a maximum range of current from very, very little current, a couple of milliamps, up to a maximum of 1 amp, 3 amps, 5 amps. And I showed how to calculate R19. I put the calculation into a spreadsheet, and R19 needs to be like 200K for 0 to 1 amp output, and so on. You can see how it goes. Right now, R19 is a 56K, which puts the output slightly above 3 amps. I've been saying all along that this is actually the layout of the 3 amp board. If you want to have an output of 5 amps, you would have to reduce it to 32K. So there's your selection. But I did something I think is better. I just replaced R19 with a 200K pot. Well, a 200K potentiometer. I'll show you how I did that. This is a 200K 10-turn pot. There we go. It's not my first choice, but it's the only one I had in the junk box. And it has 3 leads, which a potentiometer tends to have. I'm going to take one of the 3 leads, the center lead, and I'm going to bend it over until it's against that lead, one of the end leads. Then I'm going to solder it well. So I've converted it to a 2-terminal device. Then I'm going to bend the terminals down as if they exit the end of the bottom of the potentiometer. There we go. Because I'm aiming for a 2.5 amp supply, I'm going to set the potentiometer, the rheostat, to 74K. I think that'll be fine. I fashioned some leads out of some scrap wires here in the bench. One reason you shouldn't meticulously clean your bench. If you assemble kits like this, you'll have these wires laying all over. Hopefully I'll be able to put this resistor, rheostat, if you will, in place of R19. There we go. So this acts as a trimmer. If I turn this current adjust up the whole way, I can trim this, short the output, and measure the output current, and using this trimmer, adjust it to 2.5 amps. Now this board layout will be in the infamous directory below. I will mark this board number, which appears right here. And note that this change has to be made to this board number and maybe to more board numbers. I've also put XY coordinates on here, and they'll be referenced on the parts list so you can easily find the location of anything you want to find. I also will neaten up the schematic a little bit. It also has XY coordinates, and I'll have an 8.5 by 11 version of this. And this is a double wide version. You have to print it twice, cut it once on the match line, line them up, and you'll have a bigger schematic. Now, I've said that I did not consider this supply capable of 5 amps. I'll give you 2 more reasons. The first one you have to verify by doing a little studying, but a 50 volt and lower power supply that delivers 5 amps needs typically 6,000 to 12,000, I've seen 18,000 microfarads of input filter capacitors. Here we have less than 2,000 microfarads, 4 times 470. At 5 amps, there'll be so much 120 cycle ripple that it's going to upset this power supply. The second thing is all of the current that exits this power supply has to come from power negative through R5. R5 is a half ohm watt resistor. If 5 amps is provided to the output, that creates a 2.5 volt drop across R5. 2.5 volts at 5 amps is 11.5 watts. The 5 watt resistor is barely enough for a 3 amp supply. It's drastically undersized for a 5 amp supply. Now, you could reduce this to a 0.22 or 0.1, but that would then change the equation for the calculation of maximum current output.